We're going to introduce you to quantum computing, or if you already know something about it, we hope to at least tell you a few things you don't know already. I'll give a bit of the talk and then hand it over to Wolf Polak, who will give you the heart of the matter, and then he'll hand it off to me near the end. Starting with the early history, what got this field started was that certain quantum mechanical effects are not efficiently simulable on a classical computer. And if you think about that for a little bit, you can turn that around and wonder about, well, can we use those quantum effects to speed up other computations? And at first, people didn't really know what to do there. And part of that is that we are very used to a very abstract model of computation, that it's really easy to forget that all computation takes place physically. And we can remind ourselves of this by thinking about some of the ways of grounding classical computer science. In that, if you think about our models of computation, think about the Babbage engine that some of you may have seen over at the Computer History Museum. More than anything else these days, I think it is a triumph of classical mechanics. And on a more abstract level, there are Turing machines, which are not something you would build, but are very classical mechanical in the way you think about them. So what we're going to do today is try to answer, at least a little bit, the question, what would it mean if we instead grounded computation in the actual physics of the universe, namely quantum mechanics? So it took a while for people to figure out what to do there. The earliest work simply formally defined what is meant by a quantum computation, which was tricky. And then people were able to prove that a quantum computer can do anything that a classical computer can do in roughly the same amount of time, and can efficiently simulate the quantum mechanical effects that inspired people to look at this field in the first place. What else can they do? Well, the earliest quantum algorithms, and I want you to listen carefully because this is unintuitive to most people, the earliest quantum algorithms solve certain problems with certainty that classical computers could only solve efficiently with high probability. And this runs sort of counter to what most people's intuitions are about quantum mechanics, because often for people, the first bit on their knowledge about quantum mechanics is that it's probabilistic. And here we're able to do something with certainty efficiently that you can only do with high probability efficiently classically. Okay, so I'm not going to go into this, but I just wanted to start that off by suggesting that intuitions here only go so far. Thank you. These early quantum algorithms spurred what really prompted the field to take off, which was that Peter Shor figured out a polynomial time quantum algorithm for factoring in the discrete log problem. And that really startled people because that breaks all standard public key encryption systems. We'll talk a little bit more about that later. At first, this didn't worry people very much because they looked at these quantum computations and they said, there is no way you can make this robust. Quantum systems are really, really fragile, and they have bad properties, some of which we will talk about later, or at least seemingly bad properties, like no cloning. And so you're just not going to be able to do error correction. So what really got the field blooming was Shor's algorithm together with the insight as to how to do robust quantum error correction. Then around the same time that error correction was figured out, Love Grover figured out an unstructured search algorithm that was provably better than any possible classical algorithm. Shor's algorithm is just better than anything we can conceive of, at least so far, and seems likely to be better than anything we can do classically. But Grover's algorithm was actually provably better than anything you could do classically, but it has a smaller speedup. We got into this shortly after that, and it was very, very exciting. And then we got a little bit discouraged because between 1996 and about 2002, there weren't really any new algorithms that came up. There were variants on the ones I've mentioned, but there wasn't anything really new. And part of that is because it's really hard to figure out what's a good program here. Thinking about quantum algorithms just requires a very, very different sort of thinking. But since 2002, a variety of quantum algorithms have been discovered. And we'll briefly touch on some of those, but most of this will be an intro, so you'll need to look at references for the variety here. But we'll give you some hint. Okay. It might make sense in a talk on quantum computing to start off with a definition of quantum computer, but instead I'm going to tell you what it is not. So all of these devices that we use all the time make use of quantum effects. So just because a computer makes use of quantum effects does not make it a quantum computer. What quantum computing does is it actually changes our notions of information and on how you process information. So you go from logic gates to quantum logic gates, from algorithms to quantum algorithms. And you have this different information, this different processing, which is what it goes on for quantum computing. This is very different from some terminology that might sound similar, like DNA computing, where DNA is really the substrate that you're working on. But it hasn't changed the fundamental notion of information here. That's still classical information. Okay. So what are we going to do today? I'll introduce you to quantum bits and some of their properties. Then Wolf will take over and talk about multi-qubit systems, which are really the heart of the matter, and how that leads to quantum circuits. Then I'll come back and talk about a heuristic quantum algorithm called quantum annealing, talk about some implications for computer science, and then we'll wrap up. So we're going to go into quantum bits now, and I'm going to first talk about photon polarization, which might not seem very relevant, but I want you to say right at the start that photons are one way of realizing a quantum bit, a qubit. And so the properties we talk about here for photons is what you'll need to do to understand quantum bits. So let's start with a simple photon polarization setup. So you have one filter, and that filter is horizontally polarized. Now, that lets through light that's horizontally polarized, and it completely blocks light that is vertically polarized. You can play with your sunglasses and see this. Now, what if light is polarized not horizontally or vertically, but somewhere in between? Then with some probability, those photons get through. But a key property here is that if it gets through that polarization filter, then it will be horizontally polarized after that. Okay. So what happens if we now put a vertical Polaroid in there? Well, now when the photons hit the vertical Polaroid, they're all horizontally polarized because they went through that horizontal filter, and none of them can get through the vertical polarization. Okay, now I'm going to do something really stupid. I'm going to put another filter in. How could this possibly help? Because you add a filter that can only get you less light, but we already had no light, so why would I do this? Well, you start with horizontally polarized photons. After going through that first filter, now you hit a filter oriented at 45 degrees. How many of the photons get through? Well, those photons are about half horizontally polarized and about half vertically polarized. They're sort of They're at 45 degrees here. So half of them are going to get through. And now what was the key property of that Polaroid? Well, once a photon gets through, it's polarized in the direction of the Polaroid, and so it's going to be polarized at 45 degrees. Now when it hits the vertical polarizer, it now has a component in that direction, and more light gets through. Okay, simple experiment. We almost brought experimental equipment along, but, well, you can play with it. So to define a qubit in terms of photons, the polarization state of a photon can be represented as a two-dimensional vector of unit length. And we can take horizontal and vertical polarizations as a basis, and an arbitrary polarization can be expressed as a linear combination of those, as a superposition of those. And just so you know, and this will become important later, you can also have complex amplitudes, linear combinations with complex coefficients, and that corresponds to circular polarization for those of you who want a physics grounding there. And also, I'm using notation that is very, very common in quantum mechanics, but is less common elsewhere. So I'm using Dirac's ket notation. So this bar with a bracket afterwards just means vector. It's like drawing a arrow over it. So you'll see that throughout this talk. We went through what happens with measurement of a photon. The polarization filters are quantum measuring devices. And quantum measuring devices have a preferred basis. They have a preferred set of states or set of subspaces that determine what the measurement outcomes can be. So in this simple case, when you have a horizontal filter, the basis you're thinking about is horizontal and vertical. And a photon with polarization A vertical, B horizontal, will get absorbed with probability the magnitude of A squared, and will get passed through with the probability magnitude of B squared. And any photon that passes through the filter now has the polarization of that filter. Those are the key properties. Okay. So when you want to, we'll be talking about quantum bits throughout the talk. When you want to, when we're talking about that, just think of a polarized photon, okay? But any two-dimensional quantum system can be viewed as a qubit. And one other thing we'll need to do to relate it to classical computer science and the results we want to get out of this is define a computational basis. I can choose any two orthogonal states, for example, horizontal and vertical, to correspond to 0 and 1 in bits, but we have all these superpositions of bits as well to play with in quantum computation. And note that because of the complex amplitudes, we need to be a little bit careful about how we think of these things. It's tempting to say that a superposition like I've drawn there is either, and this corresponds to a 45-degree angle photon, is half vertical and half vertical and half horizontal. But that's not how we would really describe a photon, right? And that's also not that great a description of what's going on quantum mechanically. It does not mean that the particle is in the state 0 or the state 1. We just don't know which. It means that it's actually in this polarization state, and then it will interact with Polaroids in certain ways. And saying what a quantum superposition means may be philosophically tricky, but mathematically we know what's going on. And measurement of qubits is just like measurement of photons. And the key properties are that once you've measured it, it will be in the basis that it's measured. It doesn't stay in the superposition. And that means that only one classical bit can be extracted from a qubit, because you have to choose a two-dimensional basis, and you'll get one of those two outcomes. And you can't get around this by making multiple copies because of something called the no-cloning theorem. And I'm going to hand this over to Wolf now to talk about even more exciting part, which is when you get multiple qubits together.
The reason we have to have two speakers is to demonstrate superpositions. Okay, so you can't do very much with a single qubit, obviously. So the question is, what happens if you combine multiple of those together and create a larger state space? And the interesting thing and counterintuitive thing is that quantum state spaces, they combine with a tensor product as opposed to the Cartesian product, which we do classically. So classically, if you have two particles that are described by a two-dimensional vector space, then the combination of them is described by a four-dimensional space. Dimensions just add up. So if you have a basis alpha I and beta I, then classically in the Cartesian product, a system consisting of two of these spaces that are described by a space that has the union of these basis vectors. In the quantum case, that's quite different. What we have the tensor product. That means the basis consists of all pairs of basis vectors of the individual spaces. And so in this case, the dimensions add up. In this case, the dimensions of the tensor product is the product of the dimensions of the individual spaces. So what that means is that a general quantum state of n qubits is described by a 2 to the n dimensional vector space, complex vector space. So if we take a single qubit space B with a basis 0 and 1, and we construct a 2-bit system out of two of those spaces, then it'll have the basis of 0 tensor 0, 0 tensor 1, and all the combinations of these basis vectors. And since these kets are just labels here, we just write this more simply by just having the bit combinations as a label of the individual basis vectors. So we would write this as the basis for the 2-qubit state. And in general, if you have an n-qubit state, it would be a 2 to the n dimensional vector space, and we label the basis vectors by the 2 to the n possible bit patterns of the n qubits. And if we know n, it's clear how long these vectors are, so we can actually write the decimal notation, or the decimal value of this bit pattern. So, and just like individual qubits can be in a superposition state, so can multi-qubit systems. So the general n-qubit state is a linear combination or superposition of some alpha I and for all possible basis vectors. And again, we normalize this to length 1 vector. Now, the interesting thing that happens here is that you have n qubits. Each qubit is described by 2 parameters. So you have 2 n parameters. But the state actually has 2 to the n parameters. So what gives here? And it turns out that what that means is that most of the n qubit states cannot be written as the tensor product of individual qubits. And that means most states, we call those states entangled, and most states are entangled. And these are going to be very important for our quantum computation. So now the question comes, what happens when we measure states with more than 1 qubit? And we can do this by measuring qubits individually, and I show you with an example what happens if you measure the second qubit of this 3-qubit state that I've written out here. So, and it almost works like the single qubit measurement. We get 0 or 1 for the measurement of the second qubit. And if we measure 0, the state will collapse in a state that is consistent with the second qubit being 0. If we measure 1, it'll be a state that's consistent with the second qubit being 1. So it's one of the two subspaces that the whole state gets projected into. And the probability that we measure 0 or 1 is just the sum of the probabilities of the individual vectors that have the one component here. Sorry, so that would be A3 squared plus A7 squared in this case. And this looks more complicated than it really is because it's just a normalization to make this a unit length vector. Okay, so I said that entangled states cannot be written as independent qubits. Here is one particular entangled state, and it has its own name. It's called an EPR pair, and the EPR stands for Einstein, Podolsky, and Rosen. And it has this form. It's a equal superposition of these two basis vectors. And I'll just show here that this cannot be written as a tensor product of two individual qubits. And so we can assume that we had two qubits, this one here and this one here. We take the tensor product of those, and that would look like this. But we'd have to have A0, B1 to be equal to 0, which means either A0 or B1 would have to be 0. And that can't be true because this has to be non-zero and this has to be non-zero. So it's not possible to write this state as a tensor product of two single qubit states. So this state has an interesting property. We can go measure one of the two qubits and we get 0 or 1. That's easy so far. What will happen as a result of the measurement, the state will collapse into a state that's consistent with that measurement. So it will be either 0, 0 or 1, 1. Now, if we measure the second qubit, we're guaranteed to get the same result as the first measurement. So these two measurements are guaranteed to be correlated. And that bothered Einstein because in theory, these qubits could be particles, photons, and they could be at the opposite end of the universe and still be entangled. And you'd get a correlated measurement. And on the face of it, that looks like you could communicate faster than the speed of light. And it turns out, if you look at it carefully, there's actually no communication going on. You just get the correlation. But I'm not going to get into details of that. So it turns out that these states are going to be really important for the quantum computation. So how do we do quantum computation? It turns out there are three different or more models of that. I'm listing three here. There is the quantum circuit model, which is close to how we as computer science people think about it. And I'll talk about that in more detail. And the way it works is we start with a known state. We apply a number of gates, logic gates, to that state, quantum logic gates. And then at the result, we measure and we get our answer. There's adiabatic quantum computation, and Eleanor's going to talk a little bit about that, or part of that. And the way this works is we define the problem as a Hamiltonian. And so I'm not going to get into deep physics, but basically what that is a function on states that tells us what the energy of that state is. And so if that function has a minimum, that we call that the ground state. And so we define a function, a Hamiltonian, whose ground state is the solution of the problem that we're looking for. And the next thing is we're defining a simple Hamiltonian whose ground state we can easily implement. And then we slowly evolve one Hamiltonian to the other. And so if one starts in the ground state, then with a high probability, depending on how fast we move, at the end, we will be in a final state, in a ground state of the final Hamiltonian. And we can read that and get the solution to our problem. And finally, there is measurement-based quantum computation, which is quite counterintuitive. It starts with a very complex, highly entangled state. And all that happens is you measure individual qubits in that state. And the measurement you perform, the basis you perform it in, depends on previous measurements. And so just by measuring qubits, you can create an arbitrary quantum algorithm. It turns out that all of these three models of computation are, give or take a polynomial factor, are equivalent. Okay, so here's the circuit model of quantum computation. We start out with a n-qubit register, and I call it psi. And then we perform a number of transformations. And what we do is we use 1-bit or 2-bit quantum gates, transformations on either a single qubit or 2 qubits. And they collectively perform a transformation on that state, and we measure the qubits. And we need classical control to decide what to measure and how to interpret the results. The reason we call this a circuit model is because we graphically represent it in some, just like an electric circuit. But the way to think about it is not as kind of qubits going along these wires. It's more like a time axis, but that's not exactly right either. But so the idea here, we start with an initial state at this point, and we're moving left to right, performing transformation U1 on the center 2 qubits, performing U2 and U3 and U4. And mathematically, if we write this as a transformation, we have the state we apply the U1 transformation, U2 and U3 and U4. Okay. So here are a couple of quantum gates. Identity, well, that's easy enough. And the negation, that's also pretty straightforward. We can do this on a classical computer. Then it gets interesting. I wrote this T transformation. It has a parameter alpha to it. And what it does is it performs a phase shift of the quantum state. So it changes the, this is a unit factor. And so it just changes the phase of the 0 and the phase of the 1 in a different direction. That's something that you cannot do on a classical computer, obviously. And the other thing to note here is that this is really a family of an infinite number of gates, because you can do this for any alpha. You can combine multiple transformations, so this would be negation and a phase shift by 180 degrees. You can also do rotations, and whereas the T rotates about the phase axis, you can also rotate about, let's call this the value axis, so you can move from 0 to 1 and 1 to 0. And the H transformation will do this. It's like for the polarization, you moved horizontal polarization or vertical polarization to a 45-degree polarization. That's what your H transformation would do. So you have a rotation in this axis as well. And H just does the 45 degrees on our polarization. You could have an arbitrary angle transformation here. Again, there's an infinite number of possible transformations. The H has a very nice property. If you take a register that consists of all zeros, and you apply H to each one of them, you get an equal superposition of all possible basis vectors. Okay, so there's one important 2-qubit gate here. There is more, but it turns out if you have the controlled NOT gate here, together with all single qubit gates, it's a complete gate set, infinite cardinality. But it's a complete set, and you can do any quantum algorithm with that. And the controlled knot is very simple. Oh, it looks very simple anyway. It just flips the second bit if and only if the first bit is 1. And it has a special graphical notation that's shown here that we use in the circuit diagrams. And I list this observation here, and it comes from physics. I'm not going to explain why this is the case. It turns out that all quantum gates or all quantum transformations that we do are linear. In fact, they are unitary, which is a little bit stronger. And that means that all quantum computations are reversible. You can run them backwards. And it also means that all quantum gates do not dissipate energy, which doesn't mean that quantum computer is free. It probably lives in a very big refrigerator that creates microkelvins. But so there's an interesting effect now because of the linearity. If we have a superposition of many classical inputs or basis vectors representing classical values, and we have this superposition state and apply a quantum transformation to that, what will happen is we effectively perform the computation on each basis vector or on the classical value of represented by each basis vector. So to show this, we can construct an equal superposition of all possible values, and I told you earlier that the H will do that to us. And what we can do, and there's theorems that prove that for most functions, classical functions, I'm not going to define this more precisely here. For most classical functions f, what you can do is you can define a quantum algorithm, a unitary transformation, which is composed out of many individual gates, and that this computation will perform, this quantum algorithm will compute f with efficiency comparable to the classical computation. And the way we typically define those is the UF is a transformation that sends this quantum state that has x in the first part and 0 in the second part of this register, and it transforms that into a state that has x in the first part and f of x in the second part. And we need to keep x around because it has to be reversible. So now what happens is if we take the superposition state here, we have all possible inputs x and the output 0, and apply UF to it. What we'll get is we get a superposition of all possible inputs and their function value. So it looks on the face of it that we've done an exponential number of computations here by just running that function once. That seems pretty amazing, except it's not directly very useful. And I show you why. If we take the example of the logical AND, there's a function, quantum transformation that computes U AND. So it sends x, y, and 0 into x, y, and x and y. And now if we do this to a superposition, which I've written out here, of all possible 2-bit combinations followed by 0, well, what we get is all 2-bit combinations, that's our input part, and the conjunction. Now, that looks nice, but what happens if we measure? We need classical information out of it eventually. If we measure the state, and no matter in what order we measure these qubits, we end up getting one row of this, one basis vector here, and we don't even know which one we get. So if you think of this as the truth table of AND, by doing the measurement, we can compute it in one step, but by doing the measurement, we get a random row of that truth table, which is not particularly useful. Okay, so I'll show you a slightly more useful example, and it gets a little bit subtle here. So there is a quantum Fourier transform, which is an efficient algorithm. Let me explain how it works, because it's slightly different from the use of f that I've shown you. So if f is a classical Fourier transform, which takes some complex vector A and produces the Fourier transform of it, then there is a efficient quantum algorithm, I call it Q, which takes any superposition here that has the coefficients of vector A and transforms it in a superposition of all possible values j, basis vectors j, that have the coefficients which are the Fourier transform of that vector. So, and we can use that to make use of the quantum parallelism that we talked about earlier. And so one way to do that is to compute the period of a function. So if you have a periodic function f, and you have a uf that computes that function, then we know we can efficiently compute a superposition of all I together with f sub I, which has some constant amplitude each. So we can efficiently compute this. We know from the previous slide that state in of itself is not very useful. But what we can do is we can measure the second part of this register, the f sub I part. And if we do that, we get a random value. We don't know what we get. Anything that's in the range of f. But the state collapses into something interesting. The state collapses into a superposition of all basis vectors here, where most coefficients are 0, and only the coefficients are non-zero if f maps I into x. Now, it turns out if you take this vector A, so A, the vector of all coefficients here, and you apply the quantum Fourier transform to that, you get another vector of coefficients, a superposition of all vectors j, where most coefficients are 0, except for those where j is a multiple of the frequency of the function f. That's what the Fourier transform will do for you. And it turns out if you measure j, you get some multiple of the frequency, and you can use classical algorithms to actually compute the real frequency or the period of that function. And that's the essence of Shor's algorithm. And here's Shor's algorithm on one slide. So what we know from number theory is that we can factor the number m if we can find the period of a function f defined here, where a is some random value that we pick. And if we can compute the period of f, we can factor m. And so the way Shor does this is, well, we compute f for all 2 to the n values simultaneously using the quantum parallelism. We apply the quantum Fourier transform to that. We make a reading. We get the period of the function, or we read a multiple of the inverse of the period. We use classical algorithms to try to compute the period. And that all will succeed and give us a factor of m with a very high probability. And Shor proves that. And it turns out this might fail. If it does, we'll try it again. We pick another random a, and again, with high probability, this will succeed. Okay. Right. So other quantum algorithms. Eleanor mentioned Shor's algorithm, Grover's algorithm, which we didn't put on here. So these are, so should really be Grover on here, which is a really important algorithm. The people who invented quantum computing are, excuse me.
Does the probability at all depend on the size of the prime? Of the number? That
Hang on. The size of what?
Of n.
M is the thing we want to factor. M is the number.
It is the probability of the success.
And we need enough bits to I think cover 2M or something, right? So we need a register large enough to cover 2M. So if you take your 1024-bit RSA key, or you need.
He was asking
48.
about the probability.
The probability of success depends on n.
So you may have to repeat, but you only have to repeat. The expected value grows only polynomially with the size of the number of bits of n. Yeah.
So it's probably not right.
Okay. Right, so the physicists invented this quantum computing stuff, and they, as Eleanor said, they started out because they wanted to simulate or they wanted to solve physical problems, and that's one of the big applications. We can actually simulate various physical processes, chemistry, and so on. There's a big area here. There's other cryptographic algorithms. There's Holmgren's algorithm for Pell equations that can break the Bookman-Williams crypto system. Then Van Damme's algorithm can predict some pseudo-random number generators. And people try to use lattice-based cryptography as an alternative to public key encryption, and Kuperberg has some impact on that. And then there's random walk algorithms that solve some graph theory problems, matrix product verification, and others. So, we're being computer scientists, we need to talk about complexity. And there are more complexity classes, more quantum classes too, but this is a simple diagram here. The interesting classes are EQP, that's the exact quantum polynomial time algorithms, and BQP, bounded error quantum polynomial time algorithms, and they fit in this diagram here. All these inclusions are known to be proper, and we don't know anything between NP and BQP, and the idea that this exponential quantum parallelism solves all your NP problems is not quite true and unlikely to be true, but we don't know yet. So, I mean, these are the some of the important known relations here. Okay, to make this all work, we need to, as Eleanor said, the quantum state is kind of finicky and we need to preserve it. So we need to have an implementation that tries to prevent errors. And if we can't prevent errors, we have to do error correction. And as Eleanor said, it was first thought to be unlikely that this is at all possible. But now we have a really very good theory, and it works really well, and it's extremely surprising because essentially what you do is you do some quantum measurements, and based on the result of the measurements, you do a you do another measurement, and effectively what happens as a result of that, you project a state that has an error in it onto a state that has no error, which seems like really magic. And again, Steen and Shor, Caldebank came up with the first error, and now it's an extremely well understood theory. Okay, so another thing we need to do is worry about fault tolerance, because you can implement error correction algorithms, for example, in such a way that if you have a single bit error, it propagates to other qubits, and you suddenly create multi-bit errors, and your computation will not work. So there's ways, you have to be careful in the way you implement error correction, for example. And finally, there is some threshold theorems which are known for the circuit model. And they're really important because essentially they say if you generate errors at a lower rate, then you can correct them. You can compute forever. So, and that's important because you don't want to have limits on how many steps you can take in your algorithm. And there's different theorems for different thresholds depending on the kind of error models, what statistics you're assuming, and what implementation you have, and so on. And turns out for adiabatic quantum computing, we don't have threshold models like that, so we don't know if that scales or under what condition it would scale.
So I want to talk a little bit about heuristic quantum algorithms. So the research in quantum computing, because we haven't had machines, quantum hardware to run on, has focused on algorithms where we can prove superiority. But if you look at all of the algorithms that are run on the world's computers, many of them, we don't have a proof that they outperform other possible algorithms. We just try them and see how they do. And if empirically they outperform other algorithms, that's what we go with. And prior to having quantum hardware, that way of evaluating quantum algorithms has been cut off from us. So as quantum hardware emerges, and we have some very early quantum annealing prototypes, I'll talk about what that is in a bit. As it emerges, we will be able to experiment with these algorithms and actually test empirically how they do. And my strong conjecture, but it is just a conjecture, is that doing so will significantly broaden the potential applications of quantum computing. It seems unlikely to me that the only algorithms for which quantum computing can provide a speed up is ones where we've been able to prove that it can provide a speed up. It's very hard to prove these things. Now, what those quantum heuristic algorithms are that will be effective is a big open question. Okay? But a fascinating one. And the most well-known quantum heuristic algorithm is quantum annealing. And as I mentioned, very early quantum annealers have been built. So I'm going to tell you a little bit about that, but I just want to make it clear that this is just one of many possible quantum heuristic algorithms. But we happen to have special purpose hardware that can run this one. So what is quantum annealing? It's a meta-heuristic for optimization. So like simulated annealing or other optimization techniques. It can be viewed, when people say quantum annealing, they can mean different things. And in one case, it can mean what I just said, a quantum algorithm that's a meta-heuristic for optimization. And in some other cases, they mean an actual physical prescription for how to implement such an algorithm. And part of the reason that there's a little bit of flow between those terms is that right now, the only quantum computational hardware we have at the moment are special purpose quantum devices which run quantum annealing. There's a question out there as to how well they run it, but that is what they are doing. Quantum annealing, like other meta-heuristics, are specified by a cost function or a energy function for the particular problem you want to solve, plus a bunch of parameters that tell you how you want to run that particular algorithm to try to solve it. And you have these heuristics for how these sorts of problems might solve better with these particular parameters. Okay? And the intuition here is that quantum annealing can outperform, for example, simulated annealing by making use of quantum tunneling, and also have this ability to have amplitude in multiple places. For extremely toy problems, we've been able to show that it outperforms simulated annealing and also more sophisticated techniques like quantum Monte Carlo methods. There is no firm evidence yet that it outperforms if you could take any possible classical algorithm there, we don't know whether quantum annealing can outperform that or not. And quantum annealing is really a family of algorithms with lots of different parameters, and so there are a lot of things to play with. Even if the most basic one ends up not being able to work, there are things like, I'll just throw out some terms, there are things like adding non-stochastic terms to the Hamiltonian that looks like it could be quite helpful, but the intuitions for exactly what terms to add and when are a subject of great research. So quantum annealing is in its infancy, but it's the first quantum heuristic algorithm that we can actually, well, it's basically the first larger scale quantum algorithm that we can run. You can run simulations on a traditional computer of what a quantum computer would do, but those give out at about 40 or a little bit more qubits. As I mentioned, for quantum annealing, you need to specify a cost function. Now that gets translated to the Hamiltonian, which Wolf mentioned before, which basically gives the energies of the possible states of the system and governs the quantum dynamics for that system. But and when we find the Hamiltonian that corresponds to the cost function, it's going to be the ground states, the lowest energy states that correspond to the solutions we want to find. So for example, you can have a spin glass where you have spins, just a classical spin glass where you have spins which are up and down, and you have a coupling of plus or minus 1 between the spins. And if you have a 3D lattice of those, that's known to be NP complete. So they're hard problems that come up here very, very quickly. So in quantum annealing, we come up with this, final problem, Hamiltonian HP, where the ground state is the state we want, or a set of states that we want to come up with, the solutions to this problem. But how do we start this algorithm? And generally, we need to choose what's called a driver Hamiltonian, and that's usually the transverse field. And the way it's probably best for you to think of this as computer scientists is that that's the Hamiltonian whose ground state is an even superposition of all of the possible states in the space. And so what happens is we start in this smear of probabilities, and it wouldn't be useful at all to measure at that point because we just get one answer at random, completely at random from that point. No information from the problem has been injected. And you slowly decrease that Hamiltonian while increasing the problem Hamiltonian. And if you do this for adiabatic quantum computation and you do that very slowly, you're guaranteed to end up in the ground state. Now, sometimes you can go just fast enough that there's a polynomial speed up and we can prove that. And then there's the question of maybe there are other cases where it will work even if we haven't been able to prove it. And then what quantum annealing, again, there's differences in how the term is used, but for typical quantum annealing cases, we don't try to run slowly. What we try to do is run really quickly and a bunch of times and see what happens, okay? And so I want to just make clear what the connection is and the differences are with adiabatic quantum computing. So there are a variety of meanings for quantum annealing. So, for example, the final Hamiltonian in an adiabatic quantum computation can be quantum. It doesn't have to be an analog of a classical cost function, okay? And that allows you to do much more complicated things, okay? But in quantum annealing, which generally we view as being applied to optimization problems, though some people use it as just a synonym for adiabatic quantum computation, but they shouldn't, in my opinion. in quantum annealing, where we're going after an optimization problem, there's the final Hamiltonian has a specific form which is mapped from a classical cost function. And again, instead of being in the slow regime, we're doing many runs in the fast regime. And also, in the adiabatic case, you want to start in the ground state. In quantum annealing, one generally starts in a thermal state with a distribution over states and have some probability of being in the ground state and probabilities being in higher states. And you may want to take advantage of thermal fluctuations there, including thermal relaxation to get you back down into the ground state in quantum annealing. Okay. Whereas in adiabatic quantum computing, none of the above holds. It's in the slow adiabatic regime, but still in cases where you can get a speed up. We know that. For adiabatic quantum computation, we have proofs that there are speed ups and that it's equally powerful to the circuit model quantum computation that Wolf was talking about. And also it's ideally done at zero temperature where you're entirely in the ground state. Though of course you have noisy implementations. Any implementation will be slightly noisy, so that's always a little bit of an approximation, which is why these things a little bit merge into each other. And also the the emerging quantum annealers, the earliest quantum annealers come from D-wave. And they run in the regime that I've mentioned for quantum annealing. So they, you can only specify final Hamiltonian that corresponds to a classical cost function, and you need to run quickly, and it's definitely at finite temperature. And I should say here that we at NASA have done some experiments with, some early experiments with quantum annealing and have a better idea of what parameters to set which work better or worse for different problems. But it's still very early days because these D-wave machines are still pretty small. Ours, which is the biggest in the world, at least outside of D-wave, has 1,097 qubits, which correspond to about 1,097 binary variables. So, you know, we can see something, but it's not going to solve practical problems that you have in the room at that small number of qubits.
What does it look like?
So there's a little chip inside, superconducting qubits, and if you come down to NASA, we can show you not the chip that's in the machine, but a sister chip, and then it's in a big cooler.
The number 1,097 kind of begs the question of what makes that an appropriate number to use.
Yeah, well, we just thought that this would be the perfect number to experiment. No.
You're deliberately choosing a bizarre number because you don't have a specific.
No. The reason is that it was a 12 by 12 grid of 8 by 8 unit cells. You're suggesting that I point to the picture here, which gives a schematic, not how they actually look, but a schematic for the connections between the qubits on here. So each of the dots is a qubit, and you'll see there are 8 in each of the squares. And the ones in the horizontal, sorry, I keep getting that backwards. The ones in the horizontal row connect to the ones above and below. The ones vertical connect horizontally to the ones across. And then the machine at NASA has a 12 by 12 grid of these. And you're going to tell me, that's not 1097, that's 1152. Well, manufacturing isn't perfect, and some of the qubits are sufficiently hard to calibrate that it's just better not to use them. So, but we have 1,097 qubits that are good, and so that's what we can play with.
What's the lithography on the chip? What's the feature size?
Ooh, I don't remember. Matt, do you know?
Well, the qubit itself is something like 700 microns, right? So it's very macro in compared to like Leibniz.
Yeah.
Okay.
So yeah, people are starting to ask questions about sort of the status of quantum hardware. We have D-Wave machines, and in the near future, both D-Wave and likely others will produce larger and better quantum annealers, so where there are more qubits, there's more connectivity, and there's better control. A number of groups are working on that. And there's also likely to be other special purpose quantum devices coming online, particularly for certain types of quantum simulation. Okay. Now, there's also the question of what about universal quantum hardware? And in superconducting qubits, a universal gate set and simple error correction has been demonstrated on 9 qubits. And near term, it's expected within the next couple years, maybe 2-3 years, 50 to 100 qubits with universal gate set, full control, which would be very, very exciting. That would be well into the realm of what we can't currently simulate classically. And so many of us are just really, really, and I'm incredibly excited. When we first started working on this, I didn't know whether we'd live to see, we didn't know if we'd live to see hardware where you could run something beyond what's classically possible. And now, with any luck, we will manage to see that, and with any luck, we'll be able to play with that. There have been impressive advances in other areas, ion traps, optical, etc. It's not clear what ultimately is going to win, but superconducting qubits are ahead at the moment. And breakthroughs are really needed to obtain a fully scalable system. Now, people will often ask, well, why are when do you think that will happen? When will you be able to factor a number of cryptographic interest? And I used to have to just speculate on my own, but this month the NSA came out and said, prepare for quantum computers. Be ready to have larger key sizes and whatever else might be necessary. But we're not quite sure what's necessary because the state of quantum resilient cryptography is a little bit unclear, but that's another talk. Okay.